Next talk giving by Hironori Sakai from JAEA. Please.
Okay, thank you. Good evening. First of all, thank you for giving me a chance to present my animal work. So before I start, this talk is not so, focused on the brand new results. So it is based on the long-term NMR work for I did for NMR in the 115 family. Okay, so my name is Hironori Sakai. I'm a researcher in JAEA at the Tokai, Japan. The Tokai is located here. So my expertise is NMR studies for strongly correlated electron systems. So today I will focus on the NMR work in the 115 family. Okay, let's start. So let me take a moment to acknowledge my many collaborators here. This talk is based on the long-term, almost more than 10 years collaboration. Okay, I'd like to thank them. So I think I don't need to detail for the serum compartment 5 here because Laura already introduced this material. So serum compartment 5 has a tetragonal crystal structure, and then the main feature in this crystal structure is the serum for the tetragonal and the square lattice network. And then serum ion is coordinated 12 indium ion like this. Then I don't think the detail, but I'd like to emphasize this material's features as 3. So this material shows us heavy fermion D-wave superconductor with highest TC. So TC is at 2.3 Kelvin at the zero field. And also pressure, magnetic field, and then chemical doping. So can tune the quantum criticality. So this material shows a strong quantum criticality fingerprints. And also, many experiments suggest these materials locate just at antiferromagnetic quantum critical point. So maybe so many experiments suggest H equals 0 and P equals 0 is the quantum critical point of this material. Okay. And also, selenium cobalt indium 5, openly so many related materials. And then most famous reference is selenium rhodium indium 5. Selenium rhodium indium 5 has an antiferromagnetism at the 3.8 Kelvin at the zero field and at ambient pressure. Then when the pressure applied to this material, the antiferromagnetism suppressed and then superconductivity induced. Then so many experiments, even microscopic probes suggest that pressure-induced superconductivity in selenium rhodium indium 5 has a very similar feature for the selenium cobalt indium 5 superconductivity. And also, the most famous material in the related 115 series is the plutonium cobalt indium 5. Plutonium cobalt indium 5 has a 18.5 Kelvin superconductivity transition. So far, probably it is the the highest TC class of this heavy fermion superconducting material. And also not only 115, like Ruderson-Popov-like phase, so selenium indium 3 and then transition metal layers, different layer stacking. So this kind of stacking gives it structural similarity 115, 218, 217, something like that. So okay, so selenium cobalt indium 5 also ideal platform for a broad systematic study. Okay, so then I'd like to introduce the NMR. Of course, the NMR can measure the many other quantities, but in this talk, I'd like to focus on the 2 quantities. So they are night shift and 1 over T1. So night shift is a static susceptibility at the nucleus site via hyperhigh coupling constant. So I draw the schematic picture in here, if we apply the external field like this, so then magnetization occurred from the electronic spin. Then this kind of electronic magnetization gives the local field at the nucleoside through the hyperfine coupling constant. So then this nuclear field, the local magnetic field, different from the external field. So then we call the difference between the external field and the local magnetic field at the nucleoside, we call the night shift. So then this night shift corresponds to the static susceptibility, the bulk magnetic susceptibility via the hyperfine coupling constant. And also, this kind of electronic magnetization gives the some kind of fluctuation of the local magnetic field. So like this. So then this this fluctuation gives the nucleosides fluctuation. We call the 1 over T1. So this is general formula of the 1 over T1. And then this 1 over T1 coming from the fluctuation of the local field. And also, I'd like to emphasize this fluctuation coming from the perpendicular component of local magnetic field at the nucleoside. Okay, so then 1 over T1 and the night shift give the so uniquely provide three. I'd like to emphasize 3 points for this NMR probe. First of all, NMR T1 gives a low energy limit excitation. So because the omega, as our NMR measurement using the megahertz radio frequency, so this megahertz order excitation corresponds to the microkelvin. So actually, this is a low energy limit practically. And also, as I already emphasized, this 1 over T1 corresponds to the perpendicular component fluctuation. So then we can decompose the component using the field orientation difference. So we can select the fluctuation component. And also, NMR is also, of course, it is local quantity. So we can detect some feature local site-to-site information. So that's why we regard this NMR probe as a microscopic probe. Okay. So, so this is a general formula 1 over T1. So I already emphasized the perpendicular component here. Then if we determine the, if we define the this quantity using the dynamical susceptibility. So imaginary part of dynamical susceptibility using this double prime, chi double prime, we can deduce the 1 over general formula of 1 over T1T. So perpendicular component of dynamical susceptibility. So important thing is that this 1 over T1T corresponds to the Q sum of the coupling constant square and chi double prime. So then, if we define the the such kind of directional 1 over T1T Ri, so the Ri corresponds to the spin fluctuations along the I-axis. So then, if we measure the 1 over T1T along the C-axis, so 1 over T1T along the C-axis corresponds to the in-plane component of fluctuation. And the same way, if we measure the 1 over T1T along the A-axis, this corresponds to the C-axis component and A-axis like this. So this is really simple formula to decompose the A-axis fluctuation and C-axis fluctuation. So then once we get such kind of quantity RA and RC and RB, so first at the first stage, we can compare the very simple formula Koringer relation. So Koringer relation gives the nuclear specific some coefficient. So if we measure the, if we determine the nucleus, so this Koringer relation gives some constant. depending on the nucleus. So then, but in the actual material, NMR-T1 is of course always differ from the ideal non-interactive value. So always 1/T1 or night shift differ from the ideal non-interacting coefficient. So the important point is the actual experimental value. How different from the Corring relation. So we call the K alpha. So if we measure the night shift and 1/T1T, we can deduce the RI. So spin fluctuation along the experimental axis. So then we can validate some K alpha. If K alpha becomes less than 1, it means the ferromagnetic enhancement exists in the material. And also, on the other hand, if K alpha larger than 1, it suggests the material shows the antiferromagnetic enhancement in the paramagnetic state. For example, in the case of selenium rhodium 5, I measured the very recently. So in the case K alpha, A-axis component, interestingly, below 30 Kelvin, it becomes larger than 1, like this. On the other hand, C-axis component is almost temperature independent. If we compare the selenium cobalt indium 5, selenium iridium indium 5, so in the case of selenium cobalt indium 5, below 40 Kelvin, K alpha becomes larger than 1, like this. And also, we also measure the selenium indium 5. Selenium indium 5 also show the K alpha larger than 1. That means at least the in-plane components show the antiferromagnetic enhancement in these materials. Okay, so let me introduce the workflow briefly. I omitted the detail for the measurement of NMR spectra and NMR site assignment. I completely omitted this. But once we determine the NMR site assignment, the spectral assignment, we can deduce the night shift from the site to site. For example, in the case of engine 1 NMR in the selenium rhodium 5, so we can deduce the night shift like this. C-axis component and the A-axis component. And then, as I already said, night shift, temperature dependent night shift corresponds to the temperature dependence of magnetic susceptibility. So then if I plot night shift against the bulk susceptibility, so we call the K-chi plot. So usually these guys show the linear relationship between the night shift and magnetic susceptibility. So roughly saying that night shift spin part corresponds to the like this. Okay. So then this slope corresponds to the hyperfine coupling constant. So we can deduce the coupling constant along the C-axis and F-axis like this. So then measure the 1/T1. So I measure the 1/T1 along the A-axis and the C-axis. For the reference, I plot together the NQR result like this. So A-axis component data is like this, and the C-axis data is like this. So as a reference, I also plot the random rhodium indium 5 state. Right? So the 1/T1 really enhances the two-order magnitude from the random material. So then if I divided the temperature, the 1/T1, we can get a 1/T1T. So this corresponds to this quantity. So then A-axis, so the same data 1/T1. So A-axis and C-axis. Then using this very simple formula, if I divided C-axis T1T by 2, this corresponds to the RA. A-axis component is fluctuation. C-axis component is like this. See, so C-axis component is like enhanced from the RA, and then temperature dependent like QES type. Then if I divided A square hyperfine coupling constant, so then we can get such kind of quantity. This corresponds to the actual spin fluctuation in this material. See, above 10 Kelvin or 5 Kelvin, C-axis component is larger than A component. But below, just above T-nail is 3.8 Kelvin or 3 Kelvin or something like that. But just above T now, the spin fluctuations anisotropy is the inverse like this. So then, okay, so I'd like to talk about the relationship between NMR T1 and the inelastic neutron scattering. Inelastic neutron scattering, so this is the data taken from the reference. In the case of cerium cobalt indium 5, at the paramagnetic state, the inelastic neutron scattering gives such kind of a chi double prime, energy dependent chi double prime. So then, this width gives the we call the gamma q, the line width of the antiparabolic spin fluctuation. So 1 over T1T, so this is a formula, but actually 1 over T1T corresponds to this slope. Because 1 over NMR 1 over T1T corresponds to the ultra low energy limit. So this slope corresponds to the 1 over T1T. So that's why so neutron scattering inelastic neutron scattering cannot measure this area, but of course, the inelastic neutron scattering map out for Q and for energy dependence, but only lowest energy region very difficult to figure out using the neutron scattering. But NMR can measure this area. And also, if I get the RI corresponds to the from the 1 over T1T, we can get such kind of quantity. So this is kind of Q averaged spin fluctuation energy. Actually, 1 over T1T corresponds to the gamma square inverse like this. Okay, so then if I convert the 1 over T1T to the gamma, so this kind of mid-electron volt. So in the case of cerium rhodium 5, the red marks cerium rhodium 5. So we can get such kind of values. And also cerium cobalt indium 5, cerium indium 5 shows such kind of spin fluctuation energy, temperature dependence of spin fluctuation energy. So interestingly, if I take the ratio of the gamma C over gamma A, in the case of cerium rhodium indium 5, the data shows that something like that. Cerium indium 5, cerium cobalt indium 5. So if this ratio larger than 1 means the spin fluctuation mean the spin wants to be XY type. And then if less than 1, the spin wants to be Ising type. So in the case of cerium cobalt, you see the gamma C over gamma A changing below 40 Kelvin, then it becomes XY type spin fluctuation. It is very interesting. So probably it is related to the spin, to the nature of the spin as superconductivity in silicon 5. We saw that. And also, if you see the energy scale of the cerium 115, so I plot the 0 to 1. But if we plot for the actinide 115 series, so this corresponds to 0 to 20. So the scale become, 1 order magnitude larger than cerium 115. So plutonium, rhodium, gallium 5, plutonium, cobalt, gallium 5 show the one order magnitude larger than the cerium 115. Probably the larger TC coming from the such kind of spin fluctuation energy. So that's a simple idea. And let me briefly show the cobalt NMR T1 again. So 1 over T1T shows something like the temperature dependence, the strong field dependence. But you can see the night shift doesn't show the field dependence like this. That means the night shift doesn't change, mean the chi zero static stability doesn't change by the field. But 1 over T1T strongly enhanced by the field, mean the if we apply the magnetic field, the chi-q response is in the mass area. So probably criticality coming from the finite. It is very simple output from this data. So night shift. So let me briefly take a bending issue in the serum cobalt indium 5. This issue is already Nick Kuro's group already suggested before we take the data, but I just want to explain how to interpret the Kekai bending. So they assume some two-fluid description, but this two-fluid description have some difficulty to interpret T1 or site difference of Q. But I took the this standpoint. So temperature dependent coupling constant. So Kki bending from the temperature dependent coupling constant. If I using the coupling dependence, so we can deduce the so I can speak, but temperature dependence coupling constant, the site to site 1 over T1 can explain this uniformly. So finally, I'd like to show the XY type spin fluctuation favor superconductivity. So this is a summary of this talk. So in the case of plutonium cobalt gallium 5, so gamma C over gamma A is really enhanced like this. So if I plot a TC against gamma C over gamma A, plutonium cobalt gallium 5 located here, serum cobalt indium 5 located here. But probably the spin fluctuation energy anisotropy gives some unique information to this, unconventional superconductivity in the 115 series. Finally, I'd like to comment on the spin fluctuation anisotropy for the high TC cuprate. High TC cuprate is a kappa spin 1/2 dynamics Heisenberg. So this spin anisotropy is Heisenberg type. So that's why if I took the such kind of quantity, always YBCO show the near the one. That corresponds to the spin. Local spin anisotropy is isotropic in this material. Okay. So that's summary. Sorry for the. Thank you very much.
Thank you very much, Dr. Sakai. Any questions, comments? Maybe I can start off with one question. So the serum rhodium indium 5 data that you showed, is that at ambient pressure or is that under pressure?
No, it is just taken very recently. It is still under ambient pressure.
Okay. Yeah. Okay. Cool.
I will keep going to take the data under pressure.
Okay.
So do you see any sign of a pseudo gap?
For serum cobalt indium 5?
Yeah. I was just curious. Yeah.
Yeah. So far, I have no such a feature, but in the case of serum rhodium indium 5, the people some research group observed some pseudo gap feature using the 1 over T1.
Mm-hmm.
But in the case of serum cobalt indium 5, of course, they show the strong field dependence. So I'm not so sure, but so far I have never seen such a feature.
Okay, thank you.
Yeah, Macari.
Yeah, thank you very much for the talk. Did I understand correctly that your measurement suggests that there is ferromagnetic component for C-axis fluctuations?
Yeah, so if I take the this kind of random phase application, so C-axis components show the less than 1 value. So if we take naively this value, probably C-axis 1 over T1 suggests C-axis suggests some ferromagnetic enhancement. But see the we cannot see any significant temperature dependence below T star. So almost temperature independence. So that's why so far I'm so considered about the ferromagnetic enhancement along Z-axis in this material.
Do you see the same thing in serum indium cobalt 5?
Yes, selenium cobalt indium 5 also show the almost a temperature independent. So maybe some form factor issue, or I'm not so sure, but anyway, so this Z-axis component shows the no temperature dependence.
So
So
it's
that's why
basically the same between rhodium, iridium, and cobalt, correct?
yes. As for Z-axis component.
Mm.
Excuse me, Hiro, this is Joe.
Yeah.
So if I understood correctly, you said that the Tokai anomaly was due to a temperature dependence of the hyperfine coupling. Is that right?
Yes, I thought this. So because if we took the two-fluid model, if I assume the such kind of two-fluid model, ROI should be correspond to such kind of formula. If I using the this formula, I cannot get the physical chi double prime using. But if I assume the temperature dependent coupling constant, so the reduced chi double prime for engine one side, engine two side is almost the same result. Because the chi double prime is the electronic quantity, so in the material, the chi double prime should be unique. So that's why if I took the two-fold model, so far in the case of selenium 115, so we cannot get any consistent result.
So what causes this temperature dependence of the hyperfine coupling?
So coupling constant, general formula is like this. So this is a kind of RKKY type. So then if there is some change of the film contact, maybe it is change of film surface, it gives us some small changes like this. So that's why coupling constant change is below coherent temperature, like probably changing the slope.
Okay, thank you.
Thank you.
Any other questions or comments for Dr. Sakai? Maybe I can sort of pose a question, maybe slightly generally. So serum cobalt indium 5 at ambient pressure actually looks critical in the sense that resistivity is linear in temperature, and one over T1T is showing some singular behavior. So if I take that as a starting point and look for anything that's singular, it seems like it's the AB plane NMR that's picking up the singularity, right? There's a strong temperature.
Right. So
and
you,
for
you
that,
can see that this data.
yeah.
So if I took the 10 Tesla data, you can see the 1 over T1T is constant.
Yeah.
This means the Fermi liquid state.
Yeah, but at the lower field, it's singular.
Yeah, it's really singular,
Yeah.
like this.
So what I'm trying to get to is that if I just isolate the singular piece, then your this Corringa ratio is suggesting that that piece is antiferromagnetic in nature because the kappa is larger than 1. Is that a
Yes.
fair?
Yeah, that's my point. So in
So
plane antiferromagnetic.
yeah, so from that perspective, maybe there's a way to reconcile putting together your data with what Laura Green talked about, namely maybe an overall picture is that there's quantum physics, and at the same time, there's some criticality that's antiferromagnetic in nature. And I wonder whether
That's an interesting point. So maybe we have to figure out what kind of local spin nature in this material.
Great. Okay, if there's no more if no further question, let's thank Dr. Sakai one more time.
Thank you very much.
Thank you.